Hey, welcome back. We're starting with logs today. Previous lesson was exponentials, and this is a pretty loaded lesson. Currently, we're on day two of logs and exponential unit. Um, yeah, this is a pretty loaded lesson, so I'm going to try and break it down as much as possible. If I have to break up the video in between, I'll do that and maybe make two videos out of it. So we'll see. All right, log functions. The objective here are to be able to define logs and then convert logs to exponentials and exponentials back to logs. Then also do the graphing and transformation of log graphs. I may not spend too much time on graphs and transformations because it's pretty much exactly the same as any other transformations, but with log graphs. Number three, super important, properties of logs, and then being able to use those properties to solve logs. Now, these properties are super important. These will not be provided on the tests and assessments, so please make a note of them, and then we will also use them how to solve logs. Here I begin. First concept here. If I have an exponential equation, very easy one here, 2 to the third power is 8. This is exponential. The inverse of exponentials, are called log functions or logarithmic functions. Because they're inverses of each other, domain and range swap positions. But let's understand how logs are written. Here's the basic definition. Logarithmic is condensed to just log. Then log is associated with a base value, followed by a value which will be equivalent to the exponent. The exponent is the answer to a log problem, versus for an exponential, exponent sits in the exponent position, obviously. So if I were to convert this to a log problem, log of the base, now base is 2 here, of the value, so log of 8 to the base 2 will be equal to 3. Basically means 2 when raised to the power of 3 would equal 8. And I've converted an exponential to a log. And now log could be converted back to exponential, so it's a loop. Another example, and we can do as many examples as possible, but if I have log to power base 5, 25, then the way I'm reading it is 5 to what power would equal 25? And we know that that answer should be 2. So the exponent itself is the answer to a log problem. In other words, if you recall exponential from last time, y equals a times b to the power of x. Graph of exponential growth looks like this. Y-intercept is 0, 1. Horizontal asymptote sits at x-axis. Domain of an exponential is all real numbers. Range of exponential would be y, where y is greater than 0, where 0 is not inclusive. Horizontal asymptote is the x-axis. Equation to that is y equals 0. Y-intercept of an exponential growth function is 0, 1. And then x-intercept, we wouldn't have any because there's an asymptote there. Now with logs, since logs are the exact inverses of exponential, log graph, and one more time, here's the exponential growth. Now a function and its inverse, like we studied in first semester, a function and its inverse are always symmetrical about this line y equals x. So with log graphs, instead of having y-intercept, we're going to have x-intercept, which is going to be 1, 0, and the domain and range will swap positions. So log graphs will look like this, where they now have a y-intercept, y-axis acting as the asymptote. So the domain for this log graph would be, the range for the exponential would be the domain of the log function. The domain here would be x, where x is greater than 0, 0 not inclusive. Range, if you notice, goes all the way to negative infinity and keeps increasing on the other side. So that would be all real numbers. It'll have a vertical asymptote instead, which is the y-axis. Equation of y-axis is x equals 0. It has an x-intercept at 1, 0, and it does not have y-intercept because there is an asymptote there. So this is the crux of logs, and how logs are inverses of exponential. Let's solve some basic, you have access to these slides, by the way. Let's solve some basic log expressions and get their answers without calculators. This question is asking me 2 raised to what power would equal 16? That should be 4, and that should be the answer to that. Next one's asking me 3 raised to what power would equal 1/9. Now, 1/9 can be written as 1 over 3 squared, and that could come in the numerator and become a negative power. So now I'm comparing apples to apples. I'm looking at this versus that. That power has to be equal to -2. Third one's asking me 4 to what power would equal 1. And then anything raised to the power of 0 is equivalent to 1. So for that matter, it doesn't even matter what the base is here. To generate a 1, power must equal 0. Fourth one's asking me 3 to what power would be equal to 3 to the half power. Here's the base. To what power would equal this value? And once you convert it, you can clearly see that the answer has to be half. Looking at the fifth one's asking me 3 to what power would equal square root of 3. Now square root is the same power as half. So when I convert it, I can clearly see this should also equal half. Now one more time, these two were the exact same questions, just written slightly differently. Let's see if we have some more examples for that very first topic we are looking at. This one's asking rewrite as exponential. So now if you know, which means I just need to convert A, B, and C into exponentials using the same technique we used. However, you want to pay attention that there's no base written down here. When no base is written down, default base is 10. 10 is also referred to as common base. So when there's no base provided, it's defaulted to 10. So this question is saying 10 to the third power must equal 1000, and I have converted it to exponent form. This question clearly has base 5 raised to the power of 3 must equal the value of the log, which is x plus 1. Now I can solve this and find x, but the question did not ask me to find it. They just want me to rewrite it. When we see natural logs, ln is referred to as natural log. The reason it's called natural log is because the default base to natural logs is e. In other words, log base e is referred to as ln, natural log, because e is a natural number. We talked about e in a previous lesson on exponents and how e, mathematician Euler came up, is responsible for getting to that number, and its value is 2.718, so on and so forth. So default base here is e. Whenever you see natural log, just know you can write down an e here, or base is e. Hence, this question is saying e raised to the power of 1.946 is approximately equal to 7, and I have rewritten it as exponential. This section, on the other hand, is asking me to actually evaluate without a calculator, which means find an answer to this. Like I said, if no base is provided, it's automatically 10. The question is asking 10 to what power will get me 100? 10 to the power of 2 will generate 100. This is asking 2 to what power will get me 1/8? Well, 8 can be written as 2 to the third power. And if I bring the 2 to the third power to the numerator, so I can compare apples to apples, so the bases are the same, I would have to change the power to negative, and that gives me -3. 2 raised to the power -3. This one's the same like previous. 7 to what power is equal to 7 to the power of half? Well, that's half. Like I said, natural base, the base is e. So I'm saying e to what power equals e to the power of 8, or clearly 8. Okay, one more time. If you see log of x, no base is provided, it's defaulted to 10. If you see natural log of x, base is defaulted to e. Other than that, you'll be given the bases. All right, one more time. If you want to try, pause here, try and convert these to exponentials. The answers are provided right here, but you can pause the video and see if you can quickly convert them. This is backwards, convert to logs. So to pause here, make sure you know how to convert from exponential to log. All the answers are provided. Okay. These are equations, if you notice, they're not expressions. And since we are solving equations, we're basically trying to find the value of x. These are log equations. Now for log equations, please know these two steps. First step is to isolate log, which means you just want to have log to whatever base and the value there. Nothing in the front or nothing behind this. Everything needs to be gotten rid of before we can start working with the equation. So isolate log is step one, and step two would be to convert it to exponential. Just what we've been doing in the previous questions. Now notice these three problems. In all three of these problems, log has been isolated already. There's nothing that the log is being multiplied with, and there's nothing afterwards. Of course, value has to be there. What that does is, step one has been taken care of. So I'm ready to convert it to exponential. 5 to x power must equal 125. Well, 125 can be written as 5 to the third power, so clearly x must equal 3. Number two, isolation's already been done, so let's convert it. 4 to the power of 3 halves must equal x. That's non-calculator. And what's the value of 4 to the power of 3 halves? That would be 8. How did that happen? Here are two ways. Now you have 4 3 halves. You could isolate the powers as power of power. Half times 3 is still 3 halves, so I've just written it differently. Now, half power automatically means square root. This is same as square root of 4 to the third power, which is 2 to the third power, which is 8. That's one way to do the problem. Another way to do that would be, you could also write 4 as 2 squared, but then there's already 3 halves there, which makes, you can cancel these two, which is 2 to the third, which is back to 8. That was basically a two-step problem. It just required some mental math, being really good with powers and fractions. Now, the third one here, also log is isolated, so let's move on to converting it to exponential. 81 can be written as 9 squared. If I bring it to the numerator, so both sides have the same format, I have to change the power to negative. And this gives me x plus 3 equals negative 2, and hence x equals negative 5. All right, we're still on first topic. I have something cool here listed as well. Actually, let's move on from there. Topic number 2, we'll come back to it. Graphs and their transformations. Now, I already explained the graph of logs. I'll do that one more time. So the parent log function stays on the positive side of x-axis. X-intercept 1, 0. Log graph looks like that. Actually, this is not a very good shape. It actually kind of goes like that and doesn't go up as fast. There, has a vertical asymptote right there. Yeah, there we go. Now with the transformations, say all the same rules apply. All same rules apply, which means if I have a log function here, log of x, let's say. So if the function, let's say negative a, and then log, and then we have x plus minus h, and then plus minus k, kind of like how we did in the first semester. All these numbers now that are associated with logs, have their own job. Like this negative, for example, is responsible for reflection, vertical reflection basically, reflection over x-axis. A plus minus here, that's with the x, is responsible for a horizontal shift, The horizontal shift is backwards, which means plus would make the graph shift to the left, minus would make it shift to the right. And this number, that's a standalone number at the very end, is responsible for vertical shift. Also, if there's a negative here, that negative needs to be pulled out. So if there's a negative here, this negative, then the one with the x, is responsible for reflection over y-axis, so horizontal reflection. And like I said, all the rules follow, but keep the parent function in mind. All the rules will apply to that. Let's do a couple of transformation problems. I've already explained that to you earlier, exponential, logs, and how they're inverses of each other. More properties are listed. You're very welcome to look at these properties in detail, how the domain and range, they swap, range swap, no y-intercepts here, there are no x-intercepts here, and so on and so forth. I know I'm kind of going fast over it, but we already studied this in the last lesson, and then I explained some of the basic properties earlier for logs. All right, let's do a couple of these examples. We're graphing these log functions. That's natural log, that's regular log, base 10, but the shape of the log does not change with the base. It doesn't matter what base it is, as long as it's a log question, the shape stays the same. So the first thing I'll do is I will draw parent log function. So I have an idea or a guideline of what to go off of. All right, and then clearly when I diagnose this, there's a negative in the front, so reflection there. This one's responsible, left one. All right, so left one at this point is now at the origin, but then also we have a reflection over x-axis. So I'm going to reflect it first. A reflection over x-axis would make the graph go like that. Now keeping that green dotted graph, I'm going to scoot it one to the left. It's going to pass through here. Y-intercept, vertical asymptote will also scoot one to the left. And now make sure we pass it through the origin, through its x-intercept. And the 2 is responsible for vertical stretch. So I can try and make this actual graph a little bit more steeper than the parent to accommodate the a value there. There we go. I tried to make it steeper. Okay, this is -1. So the black graph is the actual graph after reflection, stretching, and moving left 1. So if I were to list the domain of this, now domain x, where x is greater than -1, because the graph has scooted to the left, range still stays as all real numbers. Our vertical asymptote, which generally is the y-axis, also has scooted to the left. X-intercept also moved to the left 1, so now it's at the origin. And y-intercept happens to be the same in this case. Obviously, it changes with every situation. So here's a transformation graph, one example of it. The second one would be, this would make it go right 4 and up 2. Okay, as a guideline, I'm still going to keep the parent log function. Right 4, so the new x-intercept, 1, 2, 3, 4, so now I'm at 5, but then I also have to scoot up 2, so x-intercept has changed. So this point has moved over there. That's not the x-intercept anymore. So erase that. Okay. No stretching, no reflection, so same shape, just scooted up. Okay, I'm making it dotted to begin with, then I'll solidify it. And of course it's a sketch, so it's not going to be perfect, but close enough. There we go. I don't know the exact x-intercept here. We will have to do algebraically to find it. So don't worry about that part. I'm thinking I'm going to fix this graph a little bit. I'm not liking it. There. Just keep in mind the vertical asymptote was here, so vertical asymptote has also scooted 4 to the right. So 1, 2, 3, 4. So the asymptote is here. That's why I wasn't liking it, because I was crossing the asymptote. I don't want to do that. There we go. So here's the rough sketch, and let's solidify it. There we go. It's the best I could do right now. All right, so domain, of course, has changed. X, where x is greater than 4. Range is still all real numbers, and vertical asymptote has scooted to the right. 4 also. All right, x-intercept, we don't know it yet. We'll have to do it algebraically, and we still don't have y-intercept. All right, moving on to the third topic. I already explained this to you. Just remember natural log is basically log to base e, and then no log is defaulted to base 10, which automatically means base 10. And then any other log will be given. This base 10 is called the common log. All right, let's move on to the properties of logs. I have written down 7 properties here and highlighted their names. The first one's called the product property. I would highly recommend to pause the video here and copy these properties down. Like I said, they will not be provided on the assessments, so we need to be able to use them, identify them, and be able to apply them. Now the first one, I'll explain them real quick though. This one says if you identify a value, the value of the log, as a product of 2 expressions, then it can be broken down into log of the first number plus log of the second number. And I'll show you examples for sure. And that's called a product property. Please note, you have to have product here, not sum. Quotient property says if the value of the log here looks like a quotient or ratio of 2 expressions, can be broken down into a subtraction problem. Let me fix that. That's not that. Subtraction problem. Log of m minus log of n. Keep the base the same. And the third property says if you have log to a base of m, which is further raised to the power of n. So the level of a and m and n are all like 3 tiers. When that happens, this n, the power, can be brought in the very front and multiplied to the log as listed in the property. And the values will be equivalent. Change of base says that if you have any log expression, basically means if I have log of, let's say, 87 base 9. Now 9 to what power will equal 87? Clearly, it's going to be a decimal answer. Instead of going that route, this will have the exact same value as log of 87 divided by log of the base, always. And that's what change of base says. You can technically change the base. If you notice, base is 9 here. But when I converted it, I didn't write any base because I've defaulted it to base 10. So the base here wouldn't matter. I could change the base to 7 and 7. As long as the base is the same, the ratio will always be the same. Whether you do log of 87 over log 9, this will be the same as log of just 87 over log of 9, which will be the same as log of, like, pick any base, 5 of 87, 7 over log base 5 of 9. All these ratios will be the exact same. So per convenience, we can change this base to whatever base we want to as long as we follow this format. So one more time, change of base says if you have base and the value, this will be equivalent to the ratio of log of the value divided by log of the base. I'll show you examples later. Then this property says if log is in the exponent, watch this one, log itself is in the exponent. But as long as the number here and the base of the log are the same, the answer will simply be the power. Then the last one says log of 1. log of 1 will always be 0. So log, no matter what base it is. Which means 5 to what power will get me 1? Well, it has to be 0. Change the base to 6. 6 to what power will get me 1? Still 1 power. Still 1. And the last one is if the base, if the base and this value is the same, the answer is simply going to be 1. Because a to the first power will equal a. So that makes sense. All right, let's use them, being able to identify them. Here we go. Oh, also know, before I start, also know all this left-hand side, all these left-hand side is the condensed side, versus the right-hand side of the formulas is the expanded version of the formula. So going from left to right, we are expanding. Going from right to left, we are compressing. And that's what this question says. It says, use the log properties to expand them. To be able to explain them, if you notice there's no base written here, which means it's defaulted to 10. Also notice how this expression is basically product of x squared and x plus 5 to the fourth. So it's the product. This is your m and that's your n. Or I can use first property, which said you could split it up into log of x squared base 10 plus log of x plus 5 base to the power of 4. So I have expanded it, but whenever you expand, please also check, can it further be expanded using any of the other properties? And this will come with practice, but if you notice there's a power here, and the third property said that power can be brought to the front. Similarly, that same property could be applied to the first term as well. And now it's completely expanded. This cannot be broken down because this is not product. That's how far we could go with it. Let's look at the second one, also expanding. This is natural log, sorry. The first thing I'm going to do is convert that square root into its power. And once I look at this new expression, this half can be brought to the front using the power pop property also. So we have half natural log of x squared plus 3. Make sure to keep this in parentheses to show that x squared plus 3 is all associated with the log. Don't drop the parentheses, number one. Number two, this 2 cannot be brought to the front because x squared plus 3 is all together. I cannot get inside of these parentheses and just pick up the 2 and move it somewhere. So this one's actually expanded to the best we could. Also, this is natural log, so just know the base is e. Obviously, we're not going to write that. Okay, if you look at this one here, this looks like the format of a ratio. That's your m and that's your n. So we should be able to use the quotient property, which says log of the numerator minus log of the denominator. So that's first. I was able to use quotient property, but then I can also use the power property. 5 times log of x to the base 2 minus log of 2x minus 1. I've expanded it as much as we could. The last one, I have natural log of 8 times x times y to the fourth. So this is all multiplication. I should be able to apply the product rule to it, which means natural log of the first number plus natural log of the second number plus natural log of y to the fourth power. One other step, we could bring this 4 and drop it here. Other than that, this is all expanded. We've expanded it to the best we can. Let's look at condensing, which means going from right to left. The condense is backwards. So you have to think in the other direction. Like this is already expanded for me, and I see subtraction sign. Subtraction should remind us of the quotient property. But before you could do that, this 3 needs to be brought back up as power. So natural log of x plus 2 minus natural log of x squared. Once I do this, then I should be able to condense it using the quotient property. This is your m, and that's the n, so I put it m over n, just like how the property said, and it's pretty condensed now. Look at part B. I see a plus and I see a minus. Now you have to go left to right, because if you look at this part, this can apply the quotient property, but I have to follow left to right. Left to right, we see this coming up first, which is the power property. How do I know that? Because this could act as m and this could act as n. So this is written in the format of log 5 m plus log base 5 x squared, n, which can be condensed into log base 5 of m times n. That's what I'm going to do, log base 5 of m times n. Then minus, all right, I'll get back with this.